Welcome to the latest episode of You Ask, We Answer, presented by What Is It About the Weather? This week's question, what is evaporative cooling?
Steam. What does that do for you? Maybe it reminds you of a warm cup of coffee or cocoa, or a hot meal on a cold winter's day, or just reminds you of certain aromas in a time of year around your house. Well, steam helped power the Industrial Revolution. Heck, I might not even be bringing you this podcast if it weren't for steam. But steam and what it's representing, which is evaporation, can also mean cooling. Seems kind of odd when you think about it. So often you think of steam with warm stuff. Let's go take a look at how steam, or more importantly, evaporation, leads to cooling.
Okay, folks, time for a little quick whiteboard science here. So we've got H2O in all its forms, ice, water, and steam or water vapor. And it's not unusual to think about when you're going from a solid state to a liquid state for there to be heat introduced. It's very normal for us to think of, oh, well, I'm melting ice and that's what gives me water. But that same process is happening when we're going from water to steam. And you think about this, I didn't have boiling water when we looked at the previous video, but when you have a pot of boiling water on the stove, the temperature of the water gets to a certain level and generally stays there, but that energy, that heat coming in, is actually what's causing the phase change. The phase change, or breaking something down from a more ordered state to a less ordered state, is what it needs a lot of energy to do that, and it's doing that through the use of heat. When it's going from a less ordered state to a more ordered state, actually it's easier, and the heat is put into the environment. So when condensation happens, or when something goes from into a frozen state, heat is introduced into the environment from the liquid itself. So that's what's going on. Now, in a real world use, if you want to take that and use it to cool something, you can do that in arid areas of the world. So if you've got a house or a building, whatever it might be, and you want to cool it off, and you're fortunate enough to live in an area where the humidity is very low, you can have a device, a lot of times they sit on the roof, that kind of looks like an air conditioning unit. And that unit sucks in the hot air from the outside, okay? And it puts it through a device that has water on it that can be evaporated. And as it goes through and creates evaporation, the cool air coming out of that process can then be introduced to the building to cool it. So again, the key is, though, that you've really got to have enough difference between what we would call the wet bulb temperature, but really the humidity level for what the air temperature is outside and inside. So if you have the differentiation in humidity for how low a temperature could get, you're able to do this and use this evaporative cooling process to cool a building. Kind of neat, huh? But let's talk about how you can maybe go and sense evaporative cooling in the world around you, no matter where you live, to get a sense of what the concept is like.
A nice hot steamy shower. Now for some of you, that may have been what that steam on the stove invoked an image of. And for most of us, it's really the easiest way to demonstrate how evaporative cooling works. You're in that nice hot steamy shower and voila, you get out, and the next thing you know, a rushing cooling sensation that fills your whole body. That is actually evaporative cooling at its finest. So you got to be thinking to yourself, there must be a way that's easier to demonstrate evaporative cooling than everybody in the family jumping in the shower at once. And yes, there is. Probably the easiest way is to take a simple alcohol swab. And if you don't have a swab, certainly some rubbing alcohol and a cotton pad will work just fine. And you take that swab, and you're really just going to want to run it across the skin. Now, most of us have had this done to us at some point in time when we've had a shot or blood drawn or something. Just take that alcohol pad and rub it on the skin. And what is actually happening when you move it away is, with the heat of your skin, that alcohol is evaporating. And that's what's creating the cooling sensation on your skin. And that works because rubbing alcohol evaporates so easily at room temperature. So actually, if you leave a jug of rubbing alcohol open, that's why it evaporates much quicker than water. Now, another option, and this gets closer to the concept of an evaporative cooler that we talked about. So if you go and you take a hair dryer, just a run-of-the-mill hair dryer, try to find one with a low setting or a cool setting, because you don't want you want it to be warm, but you don't want anybody to get hurt in this process. And it's going to get a little loud in here, but you take it and you turn it on with we take this first rag, which is just a dry white rag, and we put it in front of the hairdryer, turn it on, and we put our hand on the other side of the rag. Now, once the rag gets as warm as the air coming out of the hairdryer, the air on the other side of the rag is going to feel really warm. And it should feel generally as warm, okay, of the air coming through to the hand as if you removed the rag. Now, it's not going to be a dead-on representation because the heat does get dissipated as the air gets spread around on one side of the rag. But if you hold your hand there long enough, you will notice the heat build up, and it's roughly the same temperature as the hairdryer. Now, in contrast, if you take a wet rag, which isn't going to get blown as far, let your hand cool off, and you hold it on the other side, what you'll notice is the air coming through, because this rag is evaporating, water is evaporating as it blows through it, that it's not anywhere near as hot even after you hold your hand there a while. And you could feel it, the water, or the rag itself got a little warmer, but your hand is cooler. It's not going to be cool because we're still dealing with some pretty hot air. But conceptually, if you think about outside air, outside of a warm home being warm but nowhere near as hot as a hairdryer, blowing through a cool surface, like essentially a big, long, wet rag that's just rolling over again and again and getting remoistened, what's going on there is evaporative cooling. And that's how places in the world take advantage of that evaporative cooling to cool buildings or homes. So there you have it. That's how evaporative cooling works.
So the next time your favorite meteorologist throws around the term evaporative cooling, hopefully it'll make a bit more sense. Or the next time you experience it directly, it may be a bit more obvious. Maybe on a day when it seems like it should be raining and the air's getting cooler, but no rain's hitting the ground. The picture here even shows an example of that. We call it virga, but the evaporative process is taking place, sucking the rain out of the air before it gets all the way to the ground, and the air's getting colder.
So I hope all this explanation and demonstrations has helped you better understand why evaporation is cool.
There's your 2 white sulfur reduction.